Now in a previous video we solved the differential equation that models an LR series circuit. We solved the differential equation by separating the variables. We got the current I on one side and time t on the other side. In this video we will solve this differential equation using the integrating factor method. So to do that we get it into the standard form of a linear first order differential equation. So we want the derivative term to have nothing in front of it, so we need to divide all of this by L. So we get this equation here. So L, R and E are constants. So in general we have our first order derivative, then we have a function of the independent variable multiplied by the dependent variable. So R over L is just a constant. Well, we can consider that a function of time, but time doesn't actually come into it. That's okay. It's okay if it's a constant. And after it we have the dependent variable. In general it's called Y, but here it's I, the current. And on the right hand side we have a function of the independent variable. In general here it's X, but here it's T. But here we just have a constant actually, and that's okay. So both P of X and Q of X can be constants. Anyway, that's just some notation. Now we have to get an integrating factor for this differential equation. So what we do is we have to integrate what's in front of I. We have to in general we're integrating P of X with respect to the independent variable, which is t. Now, R over L is just a constant, so we multiply it by t when we're integrating it with respect to time. So here's our integrating factor, and we stick this integrating factor in front of the three terms of the differential equation. And we saw before that when we do that, we can write the left hand side as the derivative with respect to time of the integrating factor term, that's e to the r t over L, multiplied by the dependent variable, which is I. So again, you can check that if you just use the product rule, you will indeed get the left hand side. Next, now we just multiply both sides by dt and integrate both sides. So if we integrate d of this thing in here, we just get it, and we integrate the right hand side with respect to time. So if we integrate e to the power of something, we get it back, but then we need to divide by the coefficient of t. That's R over L in this case. So we divide by R over L, which is the same as multiplying by L over R. So the L's will cancel and we get E over R here. We also have our constant of integration from both sides. We bring that over, put them together on the right hand side. Finally, to get our current as a function of time, we multiply both sides by e to the minus RT over L. So we've e to the minus RT over L times e to the plus RT over L. That gives us 1. And then we have the constant times e to the minus RT over L. Now we have this initial condition that the current is 0 at t equals 0. So if we plug 0 in for t, we get c times 1 here, and we have I equal to 0 on the left hand side. So from that we can get our constant, which is minus e over r. So we go back to our general solution, which is this, and we plug minus e over r in for c. We can factorize out e over r, and we have then 1 minus e to the minus RT over L. And as we've seen before, as t tends towards infinity, this exponential term will go to 0, so the current is approaching e over r. So for large values of t, the circuit behaves like as if we just have a resistor in it. Because if we just have a resistor of resistance R in the circuit, then E, the voltage, equals I times R.